Assalamualaikum and salam sejahtera. Today our topic is about Zener diode. So the analysis of network employing Zener diode is quite similar to the analysis of semiconductor diode in previous section. First, the state of the diode must be determined, followed by a substitution of the appropriate model and determination of the other unknown quantities of the network. Okay. This is the symbol of a Zener diode. As you can see in the figure here, Zener diode can be represented with the terminal voltage Vz over here. So the current IDZ is the current flowing through the Zener diode is opposite from ID. This current is actually the diode current, which is designed to work in reverse bias. So in Zener diode, the current should be flowing in the opposite direction compared to an ideal diode, where the current should be flowing this way. Okay, from here to here. Okay, so this is the characteristic curve of the Zener diode. As you can see here, the operating system of Zener diode is actually in this area, in this region. So okay, now we go on to the next slide. The use of the Zener diode as a regulator is so common that three conditions surrounding the analysis of the basic Zener regulator are considered. So the analysis is first for, as you can see here, fixed quantities followed by a fixed supply voltage and a variable load, and finally a fixed load and a variable supply. Okay, so these are the conditions for Zener diode application. Okay, now we look at the first condition, where the first condition is fixed V in and fixed RL. RL is the load resistance. Okay. The simplest of Zener diode regulator networks appear in this figure. The applied DC voltage is fixed. Okay, we have to fix DC voltage, as is the load resistor. So the load resistor is also fixed. The analysis can be fundamentally be broken down into two steps. Step 1 is to determine the state of the Zener diode by removing it from the network and then calculate voltage across the resulting open circuit. And step 2 is substitute the appropriate equivalent circuit and solve for the desired unknowns. Okay, now we look at the analysis. The first step, by applying step 1 to the network, where an application of the voltage divider rule result, and we have to use voltage divider rule, and the result is V equals to VL equals to RL V in over R plus RL. So the condition is if V is greater than or equal to Vz, dz will on, Zener diode will on. But if V is less than Vz, dz will off, Zener diode will off. Okay, so the first step, we have to remove the Zener diode, and this will be open circuit. So we apply VDR or voltage divider rule across RL. So the voltage across RL is equal to this equation. Alright, now we go on to the step 2. For the network of step 2 here, the on state will result in the equivalent network. Since voltages across parallel element must be the same, so we find that VL equal to Vz. Okay, so here the theorem here, it uses KCL, Kirchhoff current law, that is current entering the node equals to current leaving the node. So from here you will get IR, that is current flowing through resistor R, equal to Iz, this current that flow through the Zener diode, plus IL, current flow through load resistance. So from here you can see Iz will be equal to IR minus IL, where IL is equal to VL over RL and IR equals to VR over R. So VR is actually voltage difference between V in and also voltage at this node. So since Vz and VL is equal, so here you can see the equation becomes V in minus VL over R. And the power dissipated by Zener diode is Pz equals to Iz times Vz. Okay, that is the condition for fixed V in and fixed RL. So now we go on to the second condition. The second condition is fixed V in and variable RL. So due to the offset voltage Vz, there is a specific range of resistor value that will ensure that the Zener is in the on state. Too small a load resistance RL will result in a voltage VL across the load resistor less than Vz, and the Zener device will be in the off state. Okay, so To determine the minimum load resistance in this figure that will turn the Zener diode on, that is by simply calculate the value of RL, that will result in a load voltage VL equals to Vz. That is V equals to VL, and it is equal to RL V in over RL plus R. This is actually by using voltage divider rule. So here you can see the equation will become Vz multiplied by RL plus R, that is by moving R plus RL to the other side, and this will equal to RL VI. So Vz over RL times RL plus R equals to V. So here, as you can see, if you multiply, you can get Vz times 1 plus R over RL. That is actually Vz multiplied by 1 over RL. So 1 over RL multiplied with this equation here, RL plus R will become 1 plus R over RL. That is equal to V in. So here R over RL equal to V in minus Vz over Vz. Okay. So if you want to find RL, the equation will be RL equals to R Vz over V in minus Vz. Alright. So any load resistance value greater than the RL obtained from this equation will ensure that the Zener diode is in the on state, and the diode can be replaced by its Vz source equivalent. The condition defined by this equation establish the minimum RL, but in turn specifies the maximum IL as IL equal to VL over RL equal to Vz over RL min. Alright. Okay. And IL min is equal to Vz over RL max. Okay. Once dz on, VR remains fixed. Okay, so the equation is here, V in minus Vz equals to VR. Since VR is fixed, IR also fixed. And the equation will become IR equals to VR over R. So by applying KCL at the figure, you will get IR equals to Iz plus IL. So Iz equals to IR minus IL. Okay. Okay. Resulting Iz min when IL max and Iz max when IL min, because IR is constant. So IL min equal to IR minus Izm, and RL max equals to Vz over IL min. So RL max is actually the maximum load resistance, where IL min is okay. Since Iz is limited to Izm as provided on the data sheet, it does affect the range of RL and therefore IL. Substituting Izm for Iz establish the minimum IL as this equation. Alright. So now we go on to the next slide, which is fixed Ri and variable Vi. For fixed value of RL, the voltage Vin must be sufficiently large to turn the Zener diode on. The minimum turn on voltage Vin equals to Vin min is determined by this equation. So Vin must be sufficiently large to turn the ZEG, and the minimum voltage to turn on is Vin equals to Vin min. So by using VDR, that is voltage divider rule, you will get this equation. So from here you can get Vin min equals to RL plus R divided by RL and multiplied by Vz. Okay. The maximum value of Vin is limited by the maximum Zener current Izm. This is Zener current. Since Izm equals to IR minus IL, okay, IR minus IL, so IR max will be equal to Izm plus IL. Okay. From here is IL equals to IR minus Izm, so IR equals to IL plus Iz. Okay. Since IL is fixed, okay, at Vz over RL, and Izm is the maximum value of Iz, so the maximum Vin is defined by Vin max equals to Vr max plus Vz. Or we can say Vin max equals to IR max multiplied by R plus Vz. Okay. So that is all, I think, for this class. If you have any question regarding this topic, please WhatsApp me. And this is the exercise that you guys can do. So we have 1, 2, 3 exercise, and this is another exercise that you guys can do. So I think that is all for today class. So thank you very much, and I will give you the next lecture for the other class. So that is all. Thank you very much. Assalamualaikum and salam sejahtera. Bye.